Today I will be discussing the application of Newton's second law, the position formula, and the energy principle to analyze and predict the motion of a spring mass system swinging in an arc while oscillating on the spring. The computational model predicted the motion of the ball with little error. The model satisfied the energy principle, and there is a difference between X and Y data for oscillation periods. I will walk you through tracker, coding the model, what the model does and shows, and finally the explanation of the what does it mean questions. Here you can see I tracked the position of the mass, starting with the calibration set to the resting position of the mass. On the graph, you can see the oscillation of the mass. I will use this data to set up my computational model, and then compare the computational predictions to my data I received here. We start by plugging in our initial conditions from tracker, including ball position, velocity, and start time. Then you have delta t, which is not changed from what was given in the videos, as well as gravitational force near the Earth's surface. Then to find the spring stiffness, we use the formula for period oscillation. Here we can manipulate this equation. Since we know the mass and the period, we can solve for the spring stiffness. Then we have to find L0, the relaxed length of the spring. Static equilibrium means the weight force, and the spring force equals 0, so we know that the magnitude of the force of gravity equals the magnitude of the force of the spring. So we get this equation, and after a little manipulating, we know that L0 equals L minus mass times gravity divided by the spring stiffness, which are all variables we know. So we get that L0 equals 0.127 meters. We also know that L equals the ball position minus the spring position, and from that we can figure out L hat and S, as you can see here. Next we will begin using the energy principle. We have chosen our mass, spring, and Earth to all be in our system, so we get that the change in energy equals the change in kinetic energy plus the change in our potential energy of the Earth plus the change of kinetic energy of the spring, and all of that equals 0. We then have to plug in the equation for each of these energies into the code. You can see those here. Now in the while loop, looping while time is below 9.307 seconds, we begin with our initial energies, and we then plug in the force of gravity and the force of the spring so we can obtain the net force. And as we have done in previous labs, we have Newton's second law and our position formula updating with every iteration through the loop. Then all of this is the same as above, just updating the spring. These lines of code calculate the energy changes by using the values we gave it above and subtracting them from the initial energies also defined above. We can then run our code and it produces this. The blue ball is our predicted position, while the red ball represents the data imported from tracker. As you can see, there is very little error in the predictions. They are not perfect because the time step used in Python was a fraction of the time steps tracked in tracker, and possibly because of drag, but drag is almost so small as to be negligible. If we watch it again and focus on the arrows, you can see the black arrow represents the gravity force, and the blue represents the spring force. You can see that while the gravity does not change in magnitude, the spring force does, since gravity is a constant force acting on the mass, while the spring force depends on the length of the spring. So, is therefore also changing unless the mass is at rest. Now we can also look more closely at the graph that Python produced. The blue line represents the change in kinetic energy, and it oscillates twice as fast as the red and green. The red represents the change in potential energy of the spring, and the green represents the change in potential energy of gravity. These two have the same period of oscillation. And finally, the yellow is all the energy summed together, which stays at 0 the entire time. What does it mean? Question 1. Is the energy principle satisfied? The energy principle is satisfied because in the beginning, with our chosen system, we said that total energy would equal 0. As you can see on the graph, the yellow line, total energy, always equals 0. So the energy principle is satisfied for the model. What does it mean? Question 2. For question 2, we were told to take two separate estimates of oscillation periods. First, by estimating the period of oscillation from the x position data, and second, by estimating the period of oscillation from the y position data. I estimated the X period of oscillation to be 1.646, which was slightly higher than the Y period of oscillation, which was 1.266. You can see the difference in the graphs to the right. The periods are actually supposed to be different. This is because for the X data, the mass is moving in a pendulum motion, whereas for the Y data, the mass is moving with a spring motion. And the formula for finding oscillation periods are slightly different for the two different motions, so it makes sense for them to be slightly different. You can see the formulas below each picture. So in conclusion, the predicted data was almost identical to the data in our experiment. The energy principle was satisfied, and the period of oscillation is different for X and Y position data.